Hello everyone. In this video, we'll build upon our basic order book and create a more advanced order execution engine that simulates trading on an EVM-based blockchain. This implementation will handle order execution, where incoming orders are matched against the order book, and will track execution details like fill prices, gas costs, and slippage. To start with, let's look at the necessary headers. We include IOStream for input and output streams, string for string operations, map for our ordered data structures, vector for storing collections, IOManip for formatting output, queue for managing pending orders, chrono for time-related operations, and thread for simulating block confirmation delays. First, we define our order struct. This is similar to our basic order book in the previous video, but with an important addition, remaining quantity. This field tracks how much of the order is still unfilled after partial executions. The struct has 5 fields: ID as an integer, price as a double, quantity as an integer, is by as a boolean, and remaining quantity as an integer. The constructor takes 4 parameters: I for id, P for price, Q for quantity, and by for the isBy flag. In the initializer list, we set remaining quantity equal to quantity, meaning when an order is first created, all of its quantity is remaining to be filled. Next, we define a fill struct. This represents the result of executing part of an order. It has 5 fields: order underscore ID to track which order was filled, fill underscore price, which is the actual price at which the trade occurred, fill underscore quantity, which is how many units were traded, gas cost, which represents the transaction cost, and slippage, which measures the difference between expected and actual price. The constructor takes 5 parameters and uses an initializer list to set all the member variables. Now we define the order execution engine class. This is the core of our execution system. The class has several private member variables. First, we have bids and asks, which are maps that associate prices with quantities, just like in our basic order book. The bids map uses STD greater of double to sort prices in descending order, so the highest bid comes first. The asks map uses default ascending order, so the lowest ask comes first. We also have a pending orders queue, which stores orders waiting for block confirmation. This simulates the real-world scenario where orders need to wait for blockchain confirmation before execution. We have an execution history vector that stores all fill objects, allowing us to track and analyze past executions. We have 2 on-chain parameters: gas price per unit, which is set to 0.001, representing the gas cost per unit traded, and block time EMS, which is set to 12,000 milliseconds, simulating a 12-second block time similar to Ethereum. The class has several private helper methods. The calculate gas cost method takes a quantity as an integer and returns the gas cost by multiplying gas price per unit by the quantity. This simulates how larger orders incur higher transaction costs. The calculate slippage method takes an expected price, an actual price, and an isBy boolean. Slippage measures how much worse the execution price was compared to what was expected. For buy orders, if isBy is true, we calculate slippage as actual price minus expected price. A positive value means we paid more than expected, which is worse. For sell orders, if isBy is false, we calculate slippage as expected price minus actual price. Again, a positive value means we received less than expected, which is worse. The match order method is the heart of our execution engine. It takes a constant reference to an order and returns a vector of fill objects, since an order might be filled at multiple price levels. We start by creating an empty vector of fills and setting a remaining variable to the order's remaining quantity. If the order is a buy order, we need to match it against asks, which are sell orders. We create an iterator pointing to the beginning of the asks map. We use a while loop that continues as long as remaining is greater than 0. The iterator hasn't reached the end, and the ask price is less than or equal to the order's limit price. This last condition ensures we only match at prices that are acceptable to the buyer. Inside the loop, we get the available quantity at the current price level. Using it second, we calculate the fill quantity as the minimum of remaining and available using a ternary operator. We get the fill price from it first. We then remove the filled quantity from the order book by subtracting fill quantity from it second. If the quantity at that price level becomes 0 or less, we erase that price level from the map using asks.erase and update the iterator. Otherwise, we increment the iterator to move to the next price level. We calculate the gas cost and slippage for this fill, then create a fill object and push it to our fills vector. We subtract the fill quantity from remaining and continue the loop. For sell orders, the logic is similar but reversed. We match against bids and we check that the bid price is greater than or equal to the order's limit price, ensuring we only match at prices acceptable to the seller. After the matching loop, if there's any remaining quantity that couldn't be filled, we add it to the order book at the order's limit price. This allows partial fills, where part of an order executes immediately and the rest stays in the book waiting for matching orders. The match order method returns the vector of fills. Now let's look at the public methods. The submit order method takes a constant reference to an order and simulates submitting it for on-chain execution. First, it prints a message showing the order details using std:count. We use the ternary operator with order.asBuy to print either buy or sell. We then simulate a block confirmation delay using sleep4. We use block time milliseconds divided by 4 to simulate a partial block confirmation time. We call match order to execute the order matching, which returns a vector of fills. We then iterate through each fill using a range-based for loop with const auto and ampersand to get a constant reference. For each fill, we push it to execution history to keep a record, and we print the fill details including order ID, fill quantity, fill price formatted to 2 decimal places using std fixed and std set precision, gas cost, and slippage. After processing all fills, we calculate the total filled quantity by summing up all fill quantities. If the total filled is less than the original order quantity, we print a partial fill message showing how many units remain in the order book. Otherwise, we print a full fill message. The add liquidity method allows market makers to add liquidity to the order book. It takes a price, quantity, and is by Boolean. If isBuy is true, we add the quantity to the bids map at that price. Otherwise, we add it to the asks map. This uses the bracket operator, which automatically creates the entry if it doesn't exist, or adds to it if it does. The print order book method displays the current state of the order book. It prints a header, then sets the output format to fixed decimal notation with 2 decimal places. It iterates through the asks map using structured bindings, destructuring each entry into price and quantity. We use a counter to limit the display to the top 5 price levels. We do the same for bids, resetting the counter first. The print execution stats method displays execution statistics. It prints the total number of fills, then iterates through execution history to calculate total gas costs, total slippage, and total volume. The getBestBid and getBestAsk methods are const methods that return the best prices. They check if the respective map is empty, returning 0.0 if so, otherwise returning the first element's price using begin and then first. In the main function, we create an order execution engine instance named engine. We then set up initial liquidity by calling add liquidity multiple times. We add sell orders at prices 50,000, 50,010, and 50,020 with quantities 10, 15, and 20 respectively. We add buy orders at prices 49,990, 49,980, and 49,970 with quantities 12, 18, and 25 respectively. These represent market makers providing liquidity. We call print order book to display the initial state. We then simulate order execution. We create a buy order with ID 1, price 50,015, quantity 30, and true for as buy. This is a large order that will partially fill against the existing asks. We call submit order with this order, which will match it against the asks and execute fills. We print the order book again to see how it changed. We create a sell order with ID 2, price 49,985, quantity 5, and false for is buy. We submit this order and print the order book again. We create another buy order with ID 3, price 50,025, quantity 8, and true for is buy. We submit this order and print the order book again. Finally, we call print execution stats to display the final execution statistics, showing total fills, total volume, total gas costs, and total slippage. We return